Hello everyone, this is Space Cafe Podcast, and I'm Marcus. Ever been in a situation where you're just so wowed by what's happening around you that you want to capture it and share it with the world? Yeah, me too. Just like the other day when I was at this amazing gathering with all these top-notch scientists and engineers from the asteroid research world. We're talking about the big brains of the global community here. And they were all at ESTEC, that's the European Space Agency's testing center in the Netherlands. A beautiful place, really. But hey, I wasn't there just to kick back and enjoy the scenery. These folks were deep in discussion about some serious space business, the next big step in planetary defense, partnering up with NASA, all to figure out how to give a potentially dangerous asteroid a little nudge off its path. NASA's already done their bit last year, smashing the DART spacecraft into the double asteroid system. And next up, we've got the European Space Agency's Hera mission, ready to take the stage, analyze the crash site, and teach us a thing or two about changing the course of celestial bodies. And now here's where my story takes a bit of a turn. As I'm sitting in the audience, completely drawn into these presentations that just kept coming one after the other, I noticed something pretty cool. Nobody was zoning out. People were on their smartphones, yes, and their notebooks. But nobody's scrolling through social media or whatever. Instead, they were all locked in, checking out graphs and numbers and presentations, and having these deep discussions. And I thought, wow, this here is the real deal. So I couldn't help myself. I snapped a photo and threw it up online, basically saying, look at these folks, 8 hours deep into presentations, and their brains are still firing on all cylinders. This is passion. This is dedication. But afterwards, it got me thinking, was it cool for me to share that moment without giving everyone a heads up? I'm still chewing on that one, even when we're in awe of what's around us. We've got to remember, there's a line, and we shouldn't cross it without asking. Or should we? I still don't know. And speaking of sharing cool stuff, we're kicking off a 4-part mini-series today, diving deep into the world of asteroid research and the incredible minds behind it. And today, we're starting off with the guy at the helm, Patrick Michel, the principal investigator from the European Space Agency's Hera mission, which is all set to launch next year.
How long do you want it to be? Just to know if I have to be talkative. I have time.
So we're skipping lunch break.
Me, I've never have a lunch.
Let's give Patrick a big Space Cafe welcome, shall we?
You know, when you worked and you fight basically for 20 years to get a mission launched, first approved and then launched, when you are close to the final stage before launch, it's really an excitement, a real excitement. Plus, we have a great team. We define the team in a way that all people know each other, appreciate each other, and therefore there is a great sense of cohesion and respect and a great atmosphere, which is needed when you work on a long project.
Wonderful. Before we talk about Hera and the mission, was there a aha moment in your life that propelled you into the realm of space exploration?
Yeah, I think what really made me aware of what we can do in space is the near mission that went to see the asteroid called Eros and made first a flyby of another object. And I was actually finishing my thesis when the first images arrived, and made me realize, that these asteroids, which are just light point from the Earth, very faint light because they just reflect the solar light on their surface, and they are very small, so they are very faint. When we go to see them, they are real little worlds. with very, very rich geological features and diversities, and it's really amazing. So we went from the stage where these bodies were just very faint light point in the sky with a telescope, you don't see them by eye, obviously, to the realization that they are not just this, and they are not just, rocks, boring rocks. They are incredible, and you need space missions for that. And then, given the way those space missions worked, they really looked like adventures. Because you have a lot. First of all, when you arrive at a new body, you go from the point where you knew basically nothing except the light to a real image. And that's gives you a feeling like explorers when they discover a new territory.
It's like the first images we got from the planets in the solar system.
Exactly.
Because of due to flybys.
Yes, but the difference with the planet is that even from the Earth, you can see some features on Jupiter, for instance.
Yeah.
Of course, when you get there, it's marvelous. But asteroids is even more than that, because from the Earth,
they're invisible.
Nothing, yeah. And then you go there, and when you get the first image, it's wow, that's new. And then the books, you change. The last year was just a drawing, and now you have a real image. And this image, so far, showed us not just a beach sand on a rock, showed us craters, grooves, landslides, really living bodies, which tell us something about how the solar system works and how it evolved, because these bodies basically are subject to many processes that change their properties over time. And we need to understand how these processes work, and the features we see now are the witness of their response to those processes. And so we need to, they tell us something. It's like we are like detectives that arrive on a crime scene, and we try to understand what happened.
Where do they come from originally?
So the asteroids, most of them are between Mars and Jupiter in a region called the asteroid belt. And this is, they are the remnants of the bricks that form the planets. And contrary to the planets, so some of them eventually went into a planet, but the rest was parked in this zone between Mars and Jupiter, where they couldn't agglomerate to form a planet, because Jupiter formed very quickly, Mars also, and therefore the material between the two planets were excited dynamically by the attraction of Jupiter on one side and Mars on the other side, and therefore the impact speed was such that they would disrupt instead of agglomerating. So the good thing with them is that because they are the remnants of the bricks that form the planet, we can understand planetary formation because they have the record of the original composition of the ingredients that form the planet, which was lost in the planet.
Is it remnants of the formation, or is it building blocks of the building process? Because, so what was first? The rock, the rubble pile, the asteroid, or was the asteroid a consequence of planet building?
No, well, it's a question of, for me, the same remnant of the building blocks, if you want, because initially the solar system was our sun surrounded by a disk of gas and dust. We call that the protoplanetary disk, and so this dust started to agglomerate and grow bodies, and we think that quickly we formed 100-kilometer size bodies in the asteroid belt. We also form quickly differentiated bodies, so bodies made of a core, an iron core, a mantle and a crust like a planet. So initially we grew bodies, so these asteroids were there. And some of them eventually agglomerated into a planet, and the others, which were born already before the planet, so that's why I call them the remnants, they were never captured in the planetary process.
So they're even older than some of the planets.
Exactly. And the advantage they have is that the planets, they are big, so they were heated. And therefore, their material was chemically transformed. Like when you put ingredients in a oven and you make a cake, when you have the cake, you don't have the recipe. Because everything was transformed. And a planet is like a cake. It's something that is cooked. So the material has lost the memory of its original composition. Asteroids, which are made of the same ingredient initially, they remain small enough They never went through this heating process.
They have the original signature.
So they have the original signature. They are the best tracers of the solar system history because they have the record of the original ingredients. And in fact, we know that the solar system was born 4.568 billion years ago. It was 4.567, but recently it went to 8. It was easier to remember, 4, 5, 6, 7. So 4.567, why do we know that? It's because we have meteorites which come from asteroids. And we could find in these meteorites the first element that condensated into the solar system. So that became solid, the first solid. And we could date them. And the date is 4.568.
And they come, where do they come from? Do they come from supernovae?
No. Well,
like the original building blocks?
The original building blocks, yeah, because the heavy elements are produced by stars. So effectively, initially, you only have hydrogen and helium from the Big Bang, and then you start to produce heavy elements when the stars explode and basically produce a lot of these heavy elements that go in the interstellar space, and then you form a new star from which these heavy elements condensate around in a disk and start to produce planets. Yes, but what's interesting with asteroids is that not only they have the record of the original solids, composition of the original solid that form the planet, so we can basically start to derive a recipe to form the planet with the right ingredients. But also we know that at the end of the formation of the Earth, there were a lot of impacts. And from our theories, it's possible that the asteroids brought to the Earth all the ingredients that made life emerge on Earth. In particular, the water and the organic molecules.
So in how far is that? That's still a theory?
Well, it's a theory.
Yeah,
I mean,
okay.
it's dynamical models of the solar system history tell us why the planets are where they are. And we have in Nice, in my laboratory, the Côte d'Azur Observatory, a model called the Nice model, because this is a model that explains the best the current architecture of the solar system, why the giant planets are there, the structure of the asteroid belt, etc. And from these models of the early solar system history, effectively, which reproduce all the observables, so that's why they are credible. They may not be the only models, but so far there is only these models are able to reproduce different constraints that usually need one model for each constraint, but which contradict the other model that reproduce the other constraint. So here, in a single model, you reproduce everything, basically. So that gives strength. And according from these models, we had a dance of planets that made a lot of mixing of the material in the solar system, which explains why we have such a diversity in composition between Mars and Jupiter. It's crazy because now between Mars and Jupiter, we discover that asteroids are not only rocky bodies made of silicates, we see also bodies made of volatiles. Even ice was discovered on the surface of bodies between Mars and Jupiter, while ice is not stable in this zone because the temperature is still too high. So they must have been formed further away and implemented in the asteroid belt, and the planetary dance allowed that, for instance. So there were a lot of things going on, and at the end of the Earth's formation, because of all this instability, there were a lot of impact. And when you make the balance of the amount of water we think asteroids contain, and if they have organic molecules that look like the molecules that make living bodies, then the scenario can hold. And that's why we do sample returns from asteroids, because we want to analyze at a level of accuracy that we cannot reach with instruments on board a spacecraft. We want to analyze in the lab the very properties of these samples and check how they relate to life, basically. And we already have some clues, because a mission called Hayabusa 2 from the Japanese Space Agency already brought back samples of a carbon-rich asteroid, and we found 20,000 organic molecules. We found amino acids.
Huh. Yeah. The building blocks.
Exactly, and we found even uracil, which is one of the bases of the RNA. So
that is crazy.
Yeah. So, of course, and now we have the OSIRIS-REx mission that returned samples recently and with a much higher mass, so we'll do even more analysis. And so these scenarios about the role of asteroids for the emergence of life tend to be confirmed, or at least to be consistent with what we find in these samples, although I must say that so far, if you put water and all the ingredients in a bowl and you
stir it up,
you don't produce Frankenstein. So there is something that we miss. We don't understand yet how from all this you generate life. But at least the ingredients are there, which I think is very interesting.
And they're out there. And this is so fascinating because if they are out there, they must be everywhere in the universe. And not just restricted to our solar system.
Absolutely. Amino acid, we find that in interstellar space. It's funny because in the 70s, some people produced amino acids in the lab and they say, oh, we produced life.
With lightning?
Yes. Yeah, absolutely. And in fact, people thought initially that if we can create amino acids in the lab, then you create life, until we discovered that effectively we have many of them in space. Experiment.
Yeah. It seemed very promising, but then it turned out not to be so promising.
Yeah. No, for the moment, we don't really understand how life forms. We know the ingredients, we know they are there. And the fact that asteroids contain them gives strength to this scenario telling us that maybe life comes from outside, was brought to the Earth by these bodies. The comets also play a role because we have two populations. Asteroids are the rocky bodies, or now we know they also can have ice and volatiles, which are essentially up to Jupiter distance. And then comets are these very cold bodies that formed outside of Jupiter region. So now we have still a dynamical distinction between the two populations, but in terms of properties, there seems to be a continuum, because the more we investigate asteroids, the more we see some common characteristics with comets, such as the activity. Sometimes we see some dust being ejected from an asteroid, and before we thought only comets were having this kind of process going on.
Wow.
So the situation becomes more complex than we thought, which is absolutely fascinating, and we have to put that in the models to see how this is possible. And in fact, these models of the early solar system effectively tell us that there was some instability that could have mixed a lot of bodies formed at very different distance from the sun, where sometimes the temperature is colder or sometimes hotter, and then mixed together, then you have a population with a large diversity.
So how old are these rocks, these asteroids? Rubble piles.
So it depends. If we talk about the composition is as old as
the solar system.
Of the solar system, yes. Now, the small ones, in terms of structure, have evolved because, in fact, most of the bodies which are smaller than 10 kilometers and maybe even a little larger are at least of second generation. Like if you put an asteroid of 10 kilometers between Mars and Jupiter, it does not survive against collisions over the age of the solar system. So if you have a 10-kilometer body now, it means that it was born by the disruption of a larger body. Okay.
Because there is too much asteroid traffic going on.
Exactly.
Okay.
Exactly. It's not as much as in the Star Wars movie, where Han Solo has to shoot on asteroids to go through the main belt. In fact, space is very large and they are very small, so the probability to randomly cross an asteroid is extremely small, and that's why we can send probes to Jupiter without zigzagging with asteroids. And that's why you need to use the laws of celestial mechanics to be able to reach an asteroid. But over astronomical timescale, effectively, they collide with each other. And therefore, when this happened, and that's actually I was the first one with some of my colleagues in Swiss to model the disruption of an asteroid. And to show that when you disrupt a big asteroid, larger than a few hundred meters in size and more, usually you first shatter it into small pieces, 10 meters in size, and then these pieces tend to follow each other and reagglomerate to form rubble piles. So to form what we call rubble piles, which is aggregates or an agglomerate of boulders held together by their own attraction. which is consistent with what we see now. So that's why we think that most of the small bodies now, which are smaller than 10 kilometers, are rubble piles, because when they are born from the disruption process, usually they are not born as intact solid pieces, but as very small pieces that come back together and form a new body.
Tell me, you mentioned OSIRIS-REx, you mentioned Hayabusa sample return missions. This is so exciting because you get to bring something back from those age-old places. So, speaking of OSIRIS-REx, because this is the most recent sample return mission, how does it feel to you that something comes back, and how's the process of opening that lid? How does that work?
Well, first of all, we live a really extraordinary moment with these missions because we're lucky. We have a lot of asteroid missions that have been done and now that are going. Even the Emirates are doing a mission to 7 asteroids, and they will land on the final one. So you have new actors in space, and I think this is really, really great. Plus, these are really adventures because so far we always have surprises. So each time we see a new asteroid, our assumptions are basically wrong. And I must say that I have a high respect, and I'm really impressed by the engineers that do the operations of spacecraft, because when we arrive to a new world, basically we discover in life that what we told them is not necessarily correct, because we still do some kind of guesses which are more and more educated, but yet we are still at an early stage in our understanding of these bodies. And for instance, the case of OSIRIS-REx, that was the same for Hayabusa 2, the Japanese mission. When the spacecraft arrived, we discovered that the body is covered of boulders everywhere on the surface. And we told the engineers, well, based on one body that was visited in 2005, you should have some smooth areas where you can land the spacecraft peacefully. and therefore, they designed an approach which had an accuracy of about 50 meters to land on the asteroids. And when we got there, we didn't find such large areas which were empty of rocks.
Wow.
Because one of the constraints was to find areas where the rocks are less high than about 1 meter. Otherwise, you break the spacecraft. And we couldn't find that. So
you would circle the asteroid and then go look for a landing spot.
Absolutely. And we had the help of a rock legend, Brian May, who is an expert of stereoscopic images.
The guitarist
of Queen, yes, who is not only an amazing guitarist, but also an amazing artist in terms of stereoscopic images. So basically, you give him 2 images taken at different angles, and he turned them into a 3D image, which is really, really good when you want to measure the height of boulders. In 3D, you do it easier,
of course,
than in 2D. And him and his Italian colleagues, Claudia Manzoni, they made 3D images of all the sampling sites that we pre-selected in OSIRIS-REx. And really, these 3D images helped us to down-select based on the rocks, heights, etc. And yet, we couldn't find any place which was smaller than 10 meters or so, larger than 10 meters or so to land. So the engineers had to revise entirely their strategy of navigation in order to increase the accuracy and to be able to land on such teeny areas at 300 million kilometers away from Earth.
At what speed?
At a few 10 centimeters per second. They have to land very slowly because you are in a very low gravity.
What is the asteroid traveling at what speed?
Oh, it's several tens of kilometers per second. So
tens of kilometers per second.
And the spacecraft is either following it on another orbit, but very close, like for the Japanese mission, or orbiting, doing flybys at very low altitude. That's what the OSIRIS-REx made spectacular images at very low altitude, and you feel like you are in an airplane and flying over a boulder field, which is totally crazy. Plus, we found that despite the fact that on these objects you don't have any atmosphere, you don't have any water, liquid water, or things that would provoke erosion, And that explains the diversity of rocks we have on Earth, volcanism, etc. On these bodies, you have nothing except solar radiations, thermal processes, and impacts. And yet, we have a big diversity of boulders. We see boulders which are really black and seem very rough and porous. And you have other rocks which are brighter and very angular, so more brittle. And we still don't understand how this is possible.
And all that research is being done as if you were to land on a flying bullet.
Yeah.
At the speed you shoot a bullet into wherever you want to shoot it, and then you find a second spacecraft, a second bullet, to rendezvous with that one and do research.
So that's for the DART mission.
Yeah.
That's for the sample return mission. We just have one spacecraft, and we try to land in order to get a sample and get it back to Earth with the constraint that you don't want to land.
Yeah, you need to talk about that. How does that sampling process work?
Yes. So in fact, what we decided in all the sample return missions to near-Earth objects was to use an approach called touch and go. Touch and go means I touch the surface, I stay the minimum time I need, and I go away. I don't land, because if you want to land, given the low gravity, and you want to dig into the surface, you need to anchor.
Yes.
Because action-reaction.
Yeah.
When I am on the Earth and I push on the surface of the Earth, the gravity is higher than the pressure I use to push. Therefore, I stay on the Earth. But when you do that on an asteroid, the simple fact that I push, I go away. So I need to anchor. And anchoring means I need to design the anchors. And designing the anchors means I need to make an assumption on the surface properties. Is it gravel? Is it sand? Is it cohesive? Is it soft? I don't know that.
Makes things very complicated.
Yeah, because you need to. The more assumptions you need, the more risk you take. So to use minimum assumption, we say, forget the anchors, because we don't know if it will be hard or soft. So that's a risk. Just try to design a sampling tool that just needs that the tool touch the surface, grab something, and go away. So in the case of the Hayabusa 2, the mechanism was a sort of a sample horn, so a tube of about 1 meter in size. When the bottom of the tube touched the surface, it launched a projectile into the tube of 5 grams at 300 meters per second. And when the projectile touched the surface, because of the low gravity, you have the dust emitted by the impact that goes back in the horn. You capture it and you go away. 1 second, takes 1 second. Of course, in that case, you can get much. The goal was to have 100 milligrams. They returned 5.4 grams, so 54 more. Great success. 54 times more. In the case of OSIRIS-REx, because it was really focused on getting the best sample and having enough mass, the goal was to have at least 60 grams. And therefore, the sampling mechanism had to be a little more sophisticated. So in that case, there was a sort of arm that would be deployed, 3 meters long. At the bottom of the arm, there is a cylinder. And when the cylinder touches the surface, it releases nitrogen gas to generate a sort of artificial wind that fluidize the material, the granular material on the surface, and capture it into the cylinder. And with some experiments that were made in parabolic flight that allowed to be in a low level of gravity, like on Bennu, we found that we could even collect 1 kilogram, and at minimum 60 grams. There were two one constraint was we needed to make sure there will be granular material on the surface, because it doesn't work on hard rock. And the second constraint was we need to have grains which are smaller than 2 centimeters in size, because the holes of the cylinder were 2 centimeters. And that was a risk. So when we arrived at the asteroid Bennu, we didn't have the resolution to check whether there were these sizes of grains. So we had to choose a sampling site based on an uncertainty on the grains sizes. So that was, it was like an adventure like Indiana Jones, because we had surprises, we had uncertainties, and eventually we could go closer. So we were more sure we had these grains on the 2 remaining sampling sites that we pre-selected. And eventually the sampling happened on October 20th, 2020. And despite the fact that we stayed 2 years around Bennu, and with a great team, the best experts in the world, okay, none of us predicted how the surface reacted to the sampling tool. In fact, the surface did not react. When the cylinder touched the surface, it went through the surface like if it was going into a fluid or melted butter. Like if there was
like
no
regolith,
strength.
like regolith on the moon.
No, the regolith on the moon is has high strength compared to that. The strength of the regolith on the moon is on the order of kilopascal. Here we are talking about less than 0.1 pascal. So what it is? 1 pascal is basically if I put a leaf on my hand, this is 1 pascal. It's nothing. When I put a leaf of a tree on my hand, I don't feel it. That's already 1 pascal. Here we are even below that.
Huh.
While on the images, we see rocks. And when I see a rock, for me, it's solid. That's strength. Yeah, no. So then we realized that in a low gravity, because they are very small, the behavior can be super counterintuitive because our intuition is based on our daily experience on Earth. So we are in a very different environment.
So you have something that appears to be a rock, but behaves like a sponge.
Yes.
Now that is
even worse than a sponge, because a sponge you still compact it. Here you just go through it. So the bottom line is the lesson learned is unless you touch the surface of an asteroid, you cannot know.
You have
what
no
will
clue.
Be behavior. However, I wouldn't be so pessimistic now because now we know that. We realize thanks to OSIRIS-REx, with Hayabusa 2 also. So now I hope that with all the missions that are occurring, we will now be able to better understand, even from images, what can be the behavior, because we can relate the images to the actual behavior thanks to these missions. And little by little, we progress in our understanding. And that's why we need those missions and to interact with them, because if eventually we want to be able to protect us from an impact, and if we want for some people to mine them, to use them as resources, we need this knowledge. And we are getting it now.
It must be such a wild moment to open that lid of that container once it lands on Earth. So how does that work? Would you want to be that person?
I'm not an expert of the sampling sample manipulation. So, but of course, I follow, because we have a possibility to watch in the team. I follow what they are doing, and it's really, really precise. I would say even at some point boring, because it's very long. Very slow. You need to be very patient. For me, it's never boring, because I always have in mind that this comes from 300 million kilometers away from, and we return that, which is incredible, because space remains hard. Every operation is hard. It's not like because we succeed, it was easy. The amount of work behind that, in particular the engineer that do the operations, is absolutely crazy. I mean, we don't realize that, but everything can fail at any moment. So I cried when I saw the parachute opening when the capsule came through the Earth. I was in live on a show, and I really cried. I was like, wow, this is it's crazy. So now, when we open the capsule, before even opening the cylinder where the samples are, in the capsule containing the cylinder, there were already plenty of dust from Bennu.
Huh.
So it was like the cylinder had an indigestion because he had too many samples. Because we knew that when we went back from the surface of Bennu, the camera with OSIRIS-REx looked at the cylinder like a cell file. Mm-hmm. And we were seeing some samples going away. They were too much. So we had a hard time to close.
There was a problem during the closing process. During that mission?
Yes.
So they couldn't close the lid on the asteroid.
Yeah.
So that was a tense moment.
Exactly. I was really scary because we are victim of our success.
Yes.
We have too many. And eventually we succeeded. But of course, within the capsule, even outside the container, there are a lot of dust, so the team needs more time to get this dust from Bennu, which is not yet the samples that were captured in the sampling tool. So it's absolutely fabulous.
So you get multiple layers of dust.
So
fascinating.
It's really fascinating noting that when we get back samples to Earth, we keep 70% for further analysis and future generation that will benefit from new instruments. So it's really a long-term investment that will occupy a lot of generations of researchers. And we only use the first 20% for the preliminary analysis. So the fact that we have a lot of them allows more preliminary analysis. So you do much more. That's fantastic.
What is the scientific community expecting from analyzing those samples?
Well, again, we are really looking into how the solar system formed, how planet formed, how life emerged on Earth. That is really the first objective, is really this one. And even we may have pre-solar grains, meaning grains that were formed before the solar system formed. And by analyzing those grains, we can better understand in which environment the solar system formed. So we go even before the solar system formation. So this is really relating to our origins, I would say. Then there are some bonus science, which I don't consider them as bonus, but some people could consider them second-order objectives, which is, of course, Bennu is one of the objects which still does not have a zero probability to impact with the Earth in about 200 years. Probability is very low, but it's not yet zero. And therefore, being able to really understand its properties allow us to be best prepared to deflect it, because we have a knowledge that we usually don't have for bodies that we discover and we need to deflect immediately, and we don't know the strengths, we don't know any properties. Here, at least for Bennu, we know how it is done, or what's composition, etc. That's also good. And also for the people interested in resources, because there is always this plan to use asteroids as sort of gas stations. Instead of using our resources from Earth, we put the minimum in
produce
a rocket,
fuel.
and then, which is actually, it looks like
Makes
science
sense.
fiction, but it makes sense. We need our resources on Earth. It costs less to bring less mass to space, and then you manufacture what you need. And since you have plenty of asteroids, as long as you are able to understand how to cope with them, which is what we are now doing, is we are still in the stage where we practice, where we by interacting with them, we learn
Their
how
behavior.
to interact. And therefore, it's not for tomorrow, but as somebody said, we need to be prepared before we need it.
Speaking of tomorrow, there will be a close encounter in 2029 with an asteroid called Apophis. There may be close encounters in the future. So the current mission that you're the principal investigator of, the Hera mission, a sister mission of DART, jointly done with NASA, between ESA and NASA, is doing some additional research as to how an asteroid could be deflected. So this is not a sample return mission. This has a different goal now.
Yes, here we are talking about planetary defense. The goal is really, although, what I always say is that asteroids, they are great. Why? And maybe that explains
They're
why.
They're great at a distance.
Yes, of course. But that explains why we have so many missions. It's because whichever is your objective, each mission feeds different communities. Like if you are interested in science, so how the solar system formed, etc. If you are interested in planetary defense, how to deflect an asteroid. If you are interested in mining, how to use resources. For now, you still need the same knowledge. What are their compositions? What are their physical properties? And how do they react to an external action? So even though the Hera mission, the DART mission have as primary objective planetary defense, which means that all the mission requirements were focused on planetary defense, the knowledge we get feed the other topics. We with Hera, we're gonna visit a binary asteroid. We have 15% of the asteroid population, which is made of binaries. Binaries are like the Earth and the Moon at small scale. Okay, so we need to understand how they form. And with the Hera mission, that's also an objective. We'll be able to better understand how they form because we'll investigate these bodies, and in particular, for the first time, we will measure the internal properties of an asteroid. That has never been done. That will be done with a radar. We will launch radio waves in the asteroid, and the way they reflect tell us the level of heterogeneity inside, which has never been done. So when we say asteroids are rubble piles, okay, rubble piles mean they are agglomerate of boulders. But what is the size distribution of those boulders? What are the size of the voids? which tell us how they really reagglomerated. And in the models of binary formation, depending on the internal properties of the small moon, the model can be different. So we'll be able to solve that. But the primary objective is effectively to understand what is the outcome of the DART impact, because DART made a superb, a successful impact on the moon.
That was last year.
Last year, the 26th of September.
It was done by NASA.
Absolutely. And they changed the time it takes for the moon to make one turn around its central body by 33 minutes. So initially the moon was taking 11 hours and 55 minutes, like our moon takes about 24 hours. And then we reduced, and now it's 11 hours and 22 minutes. So we know we deflected.
Okay, so something happened.
But we don't know more. Like, did we leave a crater on the moon? Did we reshape it? Both are possible, and both have different implications in the efficiency of the technique.
Maybe we should go back in time for a moment now for our audience who may not have all the knowledge of the DART mission, the Hera mission. So there's this joint mission. DART slammed into the asteroid in order to deflect it, and now Hera will rendezvous with the double asteroid to do measurements.
Yes,
okay.
This is a detective. So in fact, what we want is to test what we call the kinetic impactor technique, where we launch an artificial projectile that impacts at high velocity an asteroid, and another spacecraft measure the deflection and the properties of the asteroid to be able to understand why the asteroid responded the way it responded. Because if it's a sponge, it's a different response than if it's a metallic bar, for instance. And in fact, what's nice to say that all this started in Europe, actually, 20 years ago, when the European Space Agency launched studies of space missions to address planetary defense, and mandated a committee to which I belong, called NEOMAP, for Near Earth Object Mission Advisory Panel. And we were tasked to give a priority of mission to study by ESA that we consider priority to answer the problem of planetary defense. And we chose a mission called Don Quixote at the epoch, which was made of two spacecraft, a projectile called Hidalgo, a detective spacecraft, orbiting spacecraft called Sancho. And the aim was for Hidalgo to shoot on an asteroid, and Sancho would measure the outcome of the impact. Now, ESA did not have the money to implement the mission. And in the early 2010, in 2011, actually, there was a planetary defense conference in Bucharest. And I discussed with an American colleague, Andy Chang. We were actually studying together a sample return mission for ESA on a binary. And then we were discussing how could we make a rebirth of Don Quixote, but this time sharing the effort between NASA and ESA, so that will reduce the cost of each agency. And that was an epoch where NASA and ESA did not get along well, because NASA withdrew from some project of ESA, and so the trust was not there anymore. Now it's perfect, fortunately, came back. But it was an epoch which was not really great. So we were thinking we should find a scheme that allows the two parts of the project to be at least partially independent. So if you take an orbiter, it's always relevant for planetary defense, because characterizing an asteroid is part of the roadmap of planetary defense. You need to know your enemy, right? So for the orbiter, whatever happened to the projectile, it still makes sense to visit an asteroid. Now, the problem with the projectile, let's say that the orbiter does not fly. Can we just launch a projectile and measure something from the Earth? So we discussed together, and this...
At what distance?
So that's the point, is in order to do that, we need to find an object that comes enough close to the Earth when we do the job. And we need also that the deflection is quick enough that the telescope from the Earth can observe it before we lose the object. Okay. So if you shoot on a single asteroid, the speed of a single asteroid is super high. And if you make an impact even at 10 kilometers per second, you need months to measure the deflection. And the deflection is very small. It's okay for a real case. If we can do it well in advance, you don't need a big deflection. Okay, to miss
a fraction of a degree will help already.
But for a test where you want to be able to observe from the Earth, it's not possible. So this is where the binary object came into our mind, is to say, okay, now we have binary objects. If we shoot on the moon, what we knew from the system we knew, the binary system we knew at the epoch, is that the moon evolves around its central body at a few tens of centimeters per second at most.
Dimorphos is the name.
Dimorphos is the moon,
Yeah.
the moon we chose. But we are not yet there. The concept was, okay, if we take a moon and if we shoot, the deflection is almost immediate. So if we find a binary that comes close to the Earth and a telescope from the Earth observe the shadow produced by the moon when it is in front of the central body and measure the time it takes to have a second shadow, that is a second passage, that is one period. So then you can measure how long it takes for the moon to pass in front of the primary body. You do it before the impact and after the impact, and the difference tells you
This
how
is
you
crazy,
reflect it.
and that works.
And that should work. So then we said, okay, that's good concept. Let's go in the catalog of binary asteroids and see which one pass by the Earth. We gave a time scale of about 10 years or more because we knew the time to fund the mission, to implement it, at least we need 10 years. And in the catalog, we found two of them. One was the binary asteroid that we were studying for the sample return mission, and we said, oh no, we cannot take this one. And another one was Didymos, an object called Didymos with a moon which did not have the name at the epoch, so we called it Didymoon. And eventually it became Dimorphos. I like Didymoon, but it was not approved. And this object we knew was coming close to the Earth at the end of September 2022. And our colleague observers were saying at the distance where it comes, which is about 11 million kilometers, we can measure by the occultation, the shadow, before and after, and tell you what is the period change due to the impact. So that's why we chose Didymos and Dimorphos, because we knew, okay, if ESA, we decided ESA would do the orbiter and NADA the projectile. So if ESA cannot be there, at least from the Earth we'll get something. And that was a smart choice.
So you had a backup.
Exactly. And in fact, that was a smart choice because initially the plan was to have Hera arriving before DART, measuring the properties, going at 100 kilometers away from the asteroid, let DART do the impact and come back and measure the outcome.
That would have produced nice imagery also.
Of course. That was the best scenario. Unfortunately, the delegation of ESA refused the project in 2016 when it was presented at the ESA council at ministerial level that occurs every 3 years. And this is when we need approval to launch before DART.
Okay.
Unfortunately, at the last moment, one of the big countries withdrew the money. And the DG of ESA, the Director General of ESA, had no choice but to remove the project from the table. So we were all depressed.
How did that feel?
You were asking what was the best moment of my life in my career. It was the worst one. Because I was in Japan, and Jan Carnelli from ESA was at the Ministerial Council and was giving me news. And it was over 2 days. The first day, good news, we had money, and we are waiting the second day for the last part, and he didn't come. And when he called me, we cried 20 minutes together.
No.
And now I had a lot of journalists that were expecting we were approved, calling me in Japan during the night, and I had to repeat at the same time, we failed. It was terrible. And the worst for me was to receive emails of the young people who wanted to do a PhD on this, a postdoc, and I had to tell them that won't happen. And I was thinking, that's bad. The young generations, that was a great opportunity. And that's because of that in January, that was December 2016, January, I asked an appointment with the Director General of ESA, and I went with Jan Carnelli, and we asked him to not give up and to try to find a way. And he gave us the chance to optimize the mission, to possibly put it on the table of the next council, which was 3 years later, 2019. And we are able to have it approved. But now the
window
problem was we had to launch later than that and arrive 4 years, which is still okay for what we want to measure. But of course, the message would have been very different. We were both Europe and US together at the same moment.
Of course.
So, okay, we don't lose everything. Fortunately, we'll have a superb mission. And we know that what we want to measure won't have changed 4 years after the impact. That gives a lot more suspense. That gave us time to prepare better the mission. And now we have a mission. The spacecraft is integrated, is going under vibration test currently. It's superb. We have a great team, and we will be able to answer the question that Dart left, because we don't know in which state is Dimorphos anymore. If it is reshaped, if there is a crater, we don't know what is the efficiency of the Dart impact. We know the period was changed, but is it because Dimorphos is not super heavy, so it was easy to deflect it? So we need the mass of Dimorphos. We don't know what's the internal property, so why we have so much dust produced. And all this will be answered by Hera.
During your talk yesterday, you presented the exact weight of Hera. And the exact weight of Hera is 666.6 kilograms. And you related this also to your interest in heavy metal music.
Yeah.
So, what's the story behind this?
Now, the story is when I saw the number 666, I had in mind the song of Iron Maiden, 666, the number of the beast. And Hera is our beast. It's a good beast. Exactly. So no, it's I found it interesting because that comes naturally. And
say Patrick, asteroids are tricky objects. On the one hand, they may harbor traces to the origins of life. At the same time, they are the ones who will end life at some point if they slam into life-harboring planets.
That's why we try to prevent.
Exactly. In how far, if out of nowhere an asteroid happened to be on collision course next year with Earth, from your learnings, from our learnings as humans through those missions, Hera, Hayabusa, OSIRIS-REx, would we be able to do something against it?
Next year, no. Fortunately, for all we know, mostly all the objects that can cause a global catastrophe on Earth.
So we know them?
Yeah, which are objects larger than 1 kilometer in size. We know more than 90% of them. For the remaining ones, they are difficult to observe simply because they never cross the Earth when they are close to the Earth. So for them, we are okay for at least a century because our calculation of evolutions of these objects are accurate for a century. Then it's like a weather forecast. Mm-hmm. After 5 days, we lose the memory. I mean, we can't find any kind of weather. So we have the same problem of chaos. It's chaos. And recall that the impact frequency of objects of 1 kilometer is on average every 500,000 years. So it's a very low probability. This is the advantage that we have with this risk, is that this is one of the least likely natural risks that we have to face. Of course, when it happens, it has big consequences. So the second advantage is that contrary to many other risks, we have means to predict and prevent it. And that's why we are doing this. It's not because we have a threat for tomorrow. Actually, if it happened tomorrow, we cannot do anything. It's because we know that eventually on the long term, it will happen. And it takes time to be prepared, but it's feasible. So what we want is to offer a plan which is robust to the future generations so that they don't have to improvise when something happens. And it's not because it's going to happen tomorrow. It's just because it's like a pandemic. You know, a pandemic is exactly the same. It's a very low risk, okay? But when it happens, it is at international level, it has global consequences. And what the COVID pandemic told us is that we need to be prepared before it happens because there are many parameters. You have the prediction. So how do you measure the risk? Is it a dangerous virus? Do I need to do something or not? Is it a dangerous asteroid? Do I need to take care of it or not? Then how do I prevent something to happen? Oh, it's coming. What do I do? Do I confine everybody? What do I do if an asteroid comes? Do I evacuate or do I deflect? And then the decision, who decides? I am the scientist. I know an asteroid is coming. Actually, we had that with Apophis. And when Apophis was discovered in 2004, the first impact probability was super high for 2029. And a few of us were saying, just as an exercise, who do I call? Do I call Jacques Chirac, my president, George Bush in the US at the epoch, or Berlusconi in Italy? Seriously, we had these questions. And we realized, hey, wait, we don't have a protocol to face this kind of problem. So the good thing is that we didn't wait the necessity, like the pandemic, to start that.
I found the movie Don't Look Up particularly interesting. How did you?
Absolutely.
Did you like it?
I recognize myself, although I'm not humble saying that, but I think I'm better than DiCaprio answering to the journalist. But that's a skill that people need to have, and scientists, at least a few of them, who can represent the others, because effectively we are faced, and I'm frequently faced with this, which is to be interviewed for 2 minutes to explain a complex problem.
It's impossible.
Well, it's possible, but it needs training.
Yes.
And that's why it's important to train. And that's why we have these communication trainings, etc., because that will always be the case. They will ask you something in the middle of two other news which have nothing to do what you are talking about. So you need to be able to speak about a complex problem to brains which are not prepared for it, because they just heard something about an influencer in Dubai, and now you have to tell them that, oh, there is an object coming, but the probability is not sure. Already probability, they are lost. So it's important. And in this movie, this is exactly what happened when he goes on a show and the guy is lost and nobody listened to him and he's not credible. And this is something that we have to face to face. And it's complex. And the pandemic also showed that there are a lot of physicians going on TV and sometimes contradicting each other. That's bad. Science is debate. We have to debate among experts. But if we debate in front of the public, we take the public as witness, and the public has not the skill to understand the differences between the sciences. And therefore, we turn science into belief. At the end, if they don't understand, they will believe the one that has a speech that corresponds to what makes them comfortable psychologically. And that's not science anymore. So what we try to do for planetary defense is to find ways of communication that eventually lead to give the message that makes consensus. And we still have debates. We debate between us. We don't hide. It's just the fact that it's totally irrelevant to debate on a technical thing in front of people that don't have the skills to understand the techniques. And my point is to say that I don't judge the people who have to deal with the pandemic, because I realize the complexity when you are not prepared. And this is because of the realization that I feel responsible, because I know that. And I want to make sure that we do all necessary to avoid the same kind of thing for an impact risk.
Yeah. You have in front of you a book publication about the Hera mission. The Hera mission is not done yet. A book is already out there. So is this a means for you to deal with the extreme tension of the whole thing, to give yourself a little bit of an outlet?
No, in fact, it's a book that is not only about Hera, actually. I had the big honor to have been involved in almost all the space missions to asteroids so far. So I'm someone who doesn't like to experience good things alone. I like to share. And it's like when I see a beautiful sunset. I remember a sunset in California, and I was alone on the hill, and I was so depressed to be alone. I wanted to be with my wife or somebody saying, hey, look, this is funny. Or when I read a fantastic book, I want to call everybody, say, hey, listen to this sentence. I like to share. And I have so many anecdotes, so many great moments that I want to show in this book how fun is science, and how rewarding it is to take risks, tackle new challenges, and sometimes fail, and not be blocked by the first failure. It's a message to the young generation, is to tell them, you are facing a lot of challenges on Earth, okay? And we had to face challenges in space. And we succeeded. Why? Why did we succeed? It's because we take them as challenges, not as problems. And depending on how you approach, you can take a difficulty as an opportunity, or you can take an opportunity as a difficulty. And I take each difficulty as an opportunity. And when your brain is in that mood, you find solutions to apparently impossible problems. And moreover, my story tells me that you cannot do alone all you want to do. You need to be with a team. You need to have a lot of competencies in a team. You need to accept the differences. All the diversity of the human species is an enrichment. When you put that together and you are able to do a teamwork, you can solve a lot of problems. And in this book, I have chapters on Sample Return Mission when I show all the difficulties that we had to go through and how the team was able, by thinking together, were able to solve the problems. So for me, it's a message of hope. We are able to solve problems in space because we are passionate, because we see that as positive challenges. And for all the challenges that we have on Earth, if we use the same spirit, I'm sure we can find solutions. Unfortunately, currently, we are all seeing everything negative. And that's not a good approach, because you don't put all your energy as much as you do it when you have fun and you see it as challenges. And the other thing also is for the Hera mission, because we failed many times before having it done. My message is to tell the young generation, it's okay to fail. What's not okay is to think that because you failed, you are not able of anything. When you fail, you learn from your failure, and you actually, you are better, you improve. And therefore, you should use your failure as lessons to fix what happened that made you fail. And then you improve and you continue. And eventually, when you see somebody succeeding, it's not like success is a linear process. It's the outcome sometimes of big efforts. Unfortunately, now many people succeed just by taking a picture and having millions of likes. So it seems easy. But don't think that everybody that you see succeed, or when you see a space mission arriving on an asteroid, it was a smooth process. So, and that's okay. That's okay. You don't have to be perfect initially. You don't have to succeed everything initially. It takes time. My life of researchers had a lot of highs and lows, and that's fine. But eventually, if you don't stop at the first law or the second law, you can accomplish a lot of things.
I think this is a great story that you're sharing, because it speaks to our sense as humans for narratives, for stories. And to me, as a storyteller in communication, if you take a very close look at stories and how they work, you will immediately see that any good story will face a problem and show you how to get over it, how to solve it, and how to succeed. And why are we listening? Why are we compelled by such stories? We are compelled by those stories because we are learning something. We're learning something for our own lives to become better and different people. So it's the transformative moment of those moments, of those elements, of those experiences. And so I think it's super critical, and I'm completely subscribing to what you're saying. Let's make mistakes and let's talk about those mistakes, because then not only myself, but also others can learn and can become better people, better researchers.
I absolutely agree. And that's really the point of the whole book, because I have chapters on space mission, but I have chapters also on how we develop the model that tell us about the history of the Hollow Solar System. And you can see that the first models, they reproduce something, they are happy, and then boom, there is something that doesn't go with the model. So you have to go back, and that's okay. That's how we that's how we learn. That's why we improve. So this is the whole point: is to say that all these challenges that we try to tackle in space and to understand our origins, etc., they are always confronted to difficulties, to surprises, to suspense that make these stories like Indiana Jones stories, except that in Indiana Jones stories, we know he will survive because he's a hero. Here, we never know what's going to happen.
Exactly.
So that's why we have to be humble and be prepared that maybe the answer is not the one we're expecting. Maybe we'll not go through the whole thing. Yeah. And that's still okay, as long as we are perseverant, persistent,
and honest.
And honest, exactly.
And honest. The book is available already to audiences?
It is released today, 11th of October 2023, in French only.
In French?
Unfortunately.
Okay.
There may be an English translation, but maybe adapted in that case because there are some parts really speaking to the French people.
So what's the title of the book?
The title is in French or in English.
Both.
À la rencontre des astéroïdes, mission spatiale et défense de la planète. So, encounter to asteroids, space missions, and planetary defense.
Wonderful.
So I hope people will like it. And we even have a Brian May, the guitarist of Queen, picture with him inside because I want to... Brian is great to have because it shows that a rock legend can also be a superb scientist, and it can generate the curiosity to people who would not initially be curious about science,
yes,
because they wonder why
yes,
a rock legend is
yes,
so fascinated. And plus, he's really amazing when he gives me stereo images, so pairs of images I can look in 3D. I fall
Crazy.
from my chairs because they are so beautiful. So it's amazing.
2 questions I keep asking my guests. Question number 1. If you were to board a spacecraft and to go to Venus, Mars, or wherever, it will be an adventure, but it will also be a boring adventure because it's going to be a very long journey. So, you being obviously a music buff, which tune would you not want to miss on that journey? Because we have a playlist on Spotify for the aspiring space traveler, and we're building that playlist for all space travelers. And now it's your turn to introduce your one tune you wouldn't want to miss.
Oh, one tune?
Just one.
Wow, one tune. That's tough.
It doesn't necessarily need to be space related. Whatever you think you wouldn't want to miss on that journey.
That's a difficult question, but when I die, so that will work. I like that I like a song which is from Dire Straits, and that would be Tunnel of Love.
Wow, beautiful song. I love this tune.
Yeah.
Wow. Thank you.
So that would be the first choice.
Wonderful. And the last question. This podcast is called the Space Cafe Podcast. It's a coffee place where we're engaging in interesting conversations. In coffee places, you now and then have an espresso to energize yourself. Now, why don't you share an espresso for the mind with me, with your audiences, to inspire audiences with whatever kind of topic you want to pick? What could be an espresso for the mind you would like to share?
An espresso for the mind. You mean a sentence that says...
A sentence, a story, a thought, an encounter you think that could be inspiring to audiences?
Okay, I would say keep open to people and opportunities, because sometimes you meet someone that can change your life. Whether it is a loving person or, like me, a professor of physics in high school that said a sentence that changed totally my trajectory. So for me, it's really important to always be open to new things and opportunities, because sometimes your life takes a different trajectory.
Wonderful. Patrick Michel, thank you so much for the time.
Thank you. It was a pleasure.
Next week, we're headed to Torino in Italy to catch up with the key player in the Hera mission. We'll be chatting with Margherita Cardi, Vice President of Programs and Program Manager for the Hera Milani satellite at TVAC. With her team, she's been instrumental in developing Milani, one of the CubeSats aboard Hera that will analyze the double asteroid system. Our conversation took some unexpected twists, leading to insights neither of us saw coming. It's a true rendezvous of minds you won't want to miss as we delve into the nitty-gritty of asteroid research and the Hera mission. So, my friends, why don't you tune in next time as we continue to explore the wonders of the cosmos together. As always, stay curious. Bye-bye. Thanks for watching.